So, a new day, a new class. In the last class, we have seen how ODE equations we can use. Now, we'll view and we will unleash few more ODE equation in this part 2 of ODE class related to biotechnology. So, hello my fellow science enthusiasts. Welcome back to our wild journey through the enchanting realm of ODE equation and Python. Today, we are not just here for laughs. In last class we have laughed a lot. We are here to tackle a real world challenge using this mystical equations. So fasten your seat belts and get ready for some exciting science. In the previous act of our comedy, we mastered exponential growth and danced with disco loving kangaroos using ODEs. But now it's time to dive into a serious and impactful application, biotechnology and medicine. Yeah, you heard it right, real life ODE application, in which we'll try to create a modeling of drug doses in chemotherapy. I hope you all know how important chemotherapy is. Now imagine you are a brilliant scientist working on improving chemotherapy treatments, and you all know these chemotherapy treatments are for cancer patients. Chemotherapy is like double-edged sword. It kills cancer cells but can also harm healthy individuals. We need to find right balance, and that's where this ODE comes to the rescue. So let us quickly deep dive into this particular thing, in which I'll give you the first step that we need to do for this complete real life hands-on experience that we are going to do with ODE. The step 1 is defining the problem. Cancer cells grow rapidly. They actually grow very rapidly, and chemotherapy drugs aims to inhibit their growth, or if you can call it inhibit their growth. But there's the catch. We don't want to administer too much or too little of drug. Too much can be toxic, and too little won't be effectively combat the cancer, or it won't effectively combat the cancer. So how do we find the optimal doses? We cannot go too much, we cannot go too less. We need to find an optimal doses. So where the ODE is our hope. So now we'll go into the step 2. In step 2, we'll model the growth of cancer cells. As we all know how cancer cells grow, and it depends on type of cancers and many other variable features, but we will just try to model the growth of cancer cells and effect of drug using an ODE. In this case, it's the logistic growth equation combined with drug effect term. What is the logistic growth equation? Don't worry, like this is some normal math, and we are going to kind of over jump it with the use of some programming language, Python. So first thing that we need to do in this programming language is we will import numpy as np. Why import numpy? Numpy, have you heard of numpy? Numpy is a library which is widely used, especially for some drastic mathematical things that we want to do inside Python script, inside our Jupyter notebooks. There are mathematical equations which we don't want to actually code, and there are some pre-made functions inside numpy. That numpy is also used extensively for the data science task also. So even if we are going to do certain tasks related to data science, these two libraries are very useful. One is numpy and another one is pandas. So now we are importing numpy as np. Why as np? It's your choice. You can import numpy as bp, np, sp, whatever you feel better. After this, we will define the ODE function for cancer cell growth with drug effect. We'll write this function as DEF. Why we are writing DEF here? Because this DEF defines a function. So we are telling this cancer underscore growth underscore with underscore drug is a function. Please consider Python, please consider this particular name cancer growth with drug as a definition of my function. So that is why we have written DEF. Now what is inside the cancer growth with drug? We have Y, we have T, we have R, we have K, and we have drug effect. Don't worry. These are all certain parameters that we are giving for the growth of drugs. And how these parameters are used? We'll say dy dt. You must have gone through some basic maths in your 11th and 12th. If you haven't, don't worry. Just write it as it is, because it's kind of judging its growth, the growth of the cancer cells while using some mathematical formulas. You don't have to take burden on it. So dy dt will be it's with respect to time how much this growth is happening. It's like with increasing time how much it is growing. Now dy dt equals to r multiplied by y multiplied by 1 minus y divided by k minus drug effect into y. What it is doing, how it is doing, I can explain it, but it might get a overwhelmed response on a mathematical ground for you. For the timing, just consider it as a function that kind of gives you the growth of cancer cells. That's it. After doing this all things, we are returning dy dt. That is what we wanted to know. We wanted to know how much it is growing, dy dt with the respect of time, how much it is growing. And here after we will write return dy dt, it will kind of give us how much it is growing. Here r is the growth rate of cancer cells. What r is? It's the growth rate of cancer cells. K is the carrying capacity. Again I am repeating, r is the growth rate of cancer cells, k is the carrying capacity, and drug effect represents how the drug impacts cell growth. I hope you kind of understood what these variables are doing. After this, we will jump on the step 3, which is setting the stage. So let us set the stage for our experiment. Now how will you set the stage for our experiment? We will use of course next code of Python, wherein the first thing that we will do is initial cancer cell population. What cancer cell population was in an initial stage? We will consider it as y naught, y0, whatever you want to name it. You can name any variable as per your convenience, but it is a standard format that we generally use. That is why I have written it y naught is equal to 1.0. So it is the initial cell population, y naught is equal to 1.0. After this, we have time points. So let us simulate treatment for say over 30 days. Over 30 days we are simulating. So instead of having a real man in front of us and kind of trying to treating that particular man or woman, taking their life into risk, we will simulate it, this particular treatment over 30 days. How will we do this? We will use t is equal to np dot line space 0, 30, 1000. T is a kind of variable that we have given. NP numpy, we have imported numpy and as NP, and inside NP we are using one particular function of it, that is line space. Inside this we are giving 3 parameters 0, 30 because we want it for 30 days and 1000. After this we are trying to decide how much drug doses. So we will start with a low dose. So we will give initial drug dose as 0.01, very small amount of drug dose. Now we will see how it affects in the next step. We will call it as step 4, the healing power of Python. Yes. Python, our trusty companion, will help us to find the optimal drug doses. Will iterate through different doses, simulate the cancer cell growth, and measure the final cell population. Now, how we are going to do this? In the next step of codes, you can see it. What we are going to do? We are going to import another thing, that is from SciPy. SciPy again is a predefined library in which we are importing .integrate. You must have heard this term in your mathematics, integration. Don't have to worry, even if you haven't heard of it, or even if you heard of it and you have forget it, don't worry. Python has a predefined library that does this all work for you. So what we are importing from this SciPy integrate is ODEINT. So ordinary differential equation integration. Let's create a function to find the final cell population for a given drug doses. So now we are creating a function to find the final cell population for given drug doses. So again, a question for you: how do we define a function? We'll define a function by writing def in the initial phase. So again, we start with def find underscore final underscore cell underscore population. You can name this function anything you want, but I have named this function as this because it makes it feel easier to understand. Okay, this is the function doing find final cell population. Inside this, we'll give a parameter, that is drug doses, how much drug we have given initially. You remember, we have given very less amount of drug doses, right? Now we are trying to solve the ODE with the current drug doses. How will we be doing this? We'll be doing this by giving this equation wherein we are saying solution is equals to ODEINT, which is again a function that we have already seen. Inside this, we are giving this parameters. First of all, we'll see the cancer growth with drug. Take this parameter, cancer growth with drug. After that, what was our y naught, what was our t that we have just seen, and there are arguments that we are having, which is r, k, and drug doses. You all already know what these variables are doing because I have already told you. After this, we are going to return the final cell population, and hence we will write return solution -1. Now we will see the initial parameters. So you can also adjust this as per your convenience. So it's not hard and fast, but initial parameter you can adjust this as per your convenience. So here what we are giving, we are, as per my convenience, I have given r is equal to 0.2, which was the growth rate. K was 1000, which was carrying capacity. R was 0.2, which I am again repeating, it's a growth rate, how much it's growing. K is equal to 1000, which is its carrying capacity, how much it can carry. Now we'll search for the optimal drug doses. How we are going to search for the optimal drug doses? We are going to write optimal doses is equal to none. Why? What? Why? Optimal doses is equal to none because initially we are considering we don't know the optimal dose, isn't it? So initially we are saying optimal dose is equal to none. We don't know. I don't know what is the optimal dose. Now what we are going to do? We'll first of all find min final population. Min final population, that does mean minimum final population, which is equal to float. Float is a data type. Like there are different data types in computer science domain, like in Python there are different data types. Float is one of them, integer is one of them. Whenever we talk about integer, we talk about numbers from 0, 1, 2, 3, 4, 5, 6, 7, 8, these are integers. If I want 1.1, 2.1, 3.1 and things like this, I generally use floats. In integer, it cannot give 0.1, 1.1, 2.1, 1000.01, something like this. Whenever we want to talk in decimals, we generally use float. For the time being, consider this as for your ease. INF, we generally use this term for infinity. So in initial stage, we are taking it as like this. Now we'll try different drug doses for doses in NumPy or NP dot line space, wherein this for, the word for, again let me explain you, don't get confused. This for is a loop. How will I tell a loop? It's like repetitively doing certain things for doses in NP dot line spaces. So if we have a dose inside NP dot line space till the time it's inside it. So if I say for I in 1 to 10, a range of 1 to 10, it will kind of repeat from 1 to 10. So it will go into 1, okay, it will go into 2, it will go into 3, into certainly it will create the same thing 10 times. Similarly, for doses in NP dot line space, so till the time this NP dot line space, whatever its parameters are, the doses will go into each of it, and what it is going to do, it is going to find final population equals to find final cell population. Yes, so we are kind of iteratively going into it and we are trying to find the final cell population by taking the doses as one of the parameters inside this final cell population. We have already decided this particular function in the above code that we have already seen. Now we are going to check if these doses yields a lower final population. And how we are going to check? It's very simple. We are just going to introduce a condition. We say if final population is less than minimum final population, then minimum final population is equal to final population. It's so simple. Don't get into the fraction figure of it. When we say the final population is less than minimum final population, it should be the final population should, it gets updated, it gets updated. So we are iteratively trying to find it. In the end, what we are finding is optimal dose is equal to doses. So iteratively we are trying to find optimal dose, and finally the new doses that keeps on gets on updating, we are kind of finding optimal dose from it. So finally we have found the optimal drug doses. The moment we find optimal drug dose, we will say print f optimal drug doses is equal to optimal doses. So whatever optimal dose that we have iteratively found out, we will print it just to see what it is. So we have to, whenever we want to see certain things in the codes, we print things. The next step is that we have already printed it, so we have done it. We have found the optimal drug doses that minimizes the final cancer cell population. So it's not very high, it's not very low, it's optimal, and we have found it by using ODEs and Python. We can fine tune chemotherapy treatments, reduce side effects, and improve the chances of beating cancer. Isn't it very wonderful? Like, this one thing can help you to find the optimal way that you can use for the treatments of certain big disease like a cancer. But the quest continues. Our journey doesn't end here. Biotechnology and medicine are treasure troves of opportunities for using ODEs to save lives and improve patient outcome. With Python as our trusty companion, we'll continue exploring these frontiers and pushing the boundaries of science. So my fellow scientists, remember, ODE equations aren't just theoretical concepts. They are powerful tools that can change lives. All you need to do is keep coding, keep experimenting, and keep making world a better place through the magic of science. So as we celebrate our success in optimizing chemotherapy doses, it's essential to recognize that ODE equations in they are also very useful in medicine and biotechnology. So, for this we will dive into another captivating real life scenario. I hope you guys are liking this real life scenario that I am trying to make for you, just to tell you that whatever theories that we are saying, it's not just the theories, we can actually use it in the real life. So, we will see one more real life application of ODE, which is modeling the immune responses. So, for this again you have to close your eyes and you have to imagine you are now on a quest to understand and manipulate the immune system, whether it's designing vaccine, studying autoimmune diseases, or even battling a pandemic. We have seen the COVID-19 in a very early stage, just few years back. ODEs are your trusted allies for this all things. So, for this we will again use some similar terms that we have already used. We will define the problem, consider for the problem we will consider a situation where a new infectious disease is spreading. So, you have to imagine a new infectious disease is spreading. How do you predict its trajectory and assess the effectiveness of vaccination strategies? Now, ODEs offer a mathematical lens to examine this all problems that you are facing, and also it will give you its solution, ready-made solution. The ODE of immunity, for this will use a simple SIR model. You remember we have discussed about the SIR model, much like the one we explored earlier. This time it will represent the susceptible infectious recovered dynamic of an infectious disease. Got confused? Let me explain you with the codes. So, the Python code that you can see here is, we will start with importing numpy as np. We have already done it. From the last code, remember the last class we have discussed about the SIR model. If you haven't seen that very seriously, go and watch that firstly, then only come here. Now, we will define the SIR model ODE function. So, how will we do it? We will write DEF. What do we use for DEF? Why do we use DEF? I can't hear. Okay, even if you are thinking that DEF is a keyword that we are using for defining a new function, you are right. I don't know if you are even giving attention to it or not. But DEF is used for defining a new function. So, here we are defining a new function named as SIR model, SIR underscore model. You can name it anything, SIR pair, anything that you want. SIR underscore model, which gives you 4 parameters, which is y, t, beta and gamma. Inside this, we are using 3 things. In this SIR model, we are using 3 things, 3 variables, that is s, comma I, comma r. This all is made equals to y. After this, we are kind of taking, we have already seen this in certain way, we have already seen this, but I am again repeating this for your convenience. So, we have ds dt, that does mean s with respect to time we are trying to find, I with respect to time we are trying to find, and r with respect to time we are trying to find. So, we are trying to find ds dt, di dt and dr dt. So, what is ds dt? Minus beta into s into I. Similarly, with respect to time, how do we find I? Beta minus beta into s into I minus gamma into I. R with respect to time, gamma into I. And after we found all ds dt, di dt, dr dt, we are going to return ds dt, di dt, dr dt. Don't worry about the mathematical inclusion of it. Just for the time being, just write these equations. That would be more than enough. We are just trying to find out certain things. That's it. So, here beta represents the transmission rate of the disease. Beta represent the transmission rate of the disease, and gamma is the recovery rate. Now, we are going to move ahead. In the next step, we are going to set the stage. So for this, let's set up the experiment, our experiment for this infectious disease scenario. How do we set up this experiment, this particular experiment? We'll use next code of the Python, that is, we'll first of all give the initial conditions. Most of the population is susceptible, a few are initially infected. So how will we write this? We'll write this S naught initial S, I naught initial I, R naught initial R. So S naught we are considering 0.95, you can change it according to your scenario. I naught we are considering 0.05 and R naught we are considering 0.0. Now we are trying to decide the time points. So let's simulate over 200 days. So even in the code I have written 200 days. So we are trying to simulate it over 200 days. For this simulation, we are trying to write T is equal to np dot line space. NP is a NumPy library that we are using, the short form for NumPy library, and line space is a function inside NumPy library. We are using 0 for 200 days and 1000. Now since we are iterating the same thing again and again, this time points, this initial variables and all, this thing must be going inside your head. The first experiment that we have seen, the next experiment that we are seeing. So this is the second time that you are trying to like just seeing the same things, right? So now you are trying to understand, okay, that was there, it's again it's like this, okay, so next time when I get some problem statement similar to this, okay, I'm going to use this np dot line space and I'm going to give parameters like this. This is how we understand. So even if you don't get the deep mathematics of it, just try to understand why, okay, this is the use case, this is a toolkit. So for example, if this is a nail that I want to put in the wall, I'll just, so how to do it, I'll just use a hammer and just, I'll see someone, okay, he's using the hammer and he's just trying to fix the things using the hammers and nail and things like this. It's the same thing. You've seen me using np dot line space at certain places. You know, okay, this is the place where we can use np dot line space. You can use it. We have used it 2 times. Now you understand how we generally use it. Now we are going to give disease parameters. You can adjust as per your convenience. So we have given beta is equal to 0.3 and gamma is equal to 0.1. Beta was the transmission rate, gamma was recovery rate. In the next step, we are going to see how Python saves the day again. So once more Python comes to the rescue. We'll use scipys, again the same function that we have used, ODE int function to simulate the spread of the disease and access various vaccination strategies. So how we are going to do this? The next Python code that is in front of you is from scipy dot integrate import ODEINT. Now this is something that you must have inside this. It must be inside. It must come into a muscle memory in order to use them again and again and again. And these are very useful functions, especially in the biological domain. So we are creating a function to simulate the disease spread and measure its impact. So we are saying DEF, we are defining simulate underscore disease underscore spread. So this is particular function which is in which we are trying to simulate how disease spreads. So we are giving beta value, we are giving gamma value, we are giving vaccination percentage, and we are going to solve the SIR model ODE. So the solution would be equal to ODEINT function. Inside this we are going to give parameters SIR model, and we are going to give parameters of initial stages of S naught, I naught, R naught. These are all initial stages of S, I and R. We are going to give T that we have already calculated. We are going to give some argument ARGS, which is beta and gamma. After we have given all this thing, we are going to calculate the final fraction of the population that remains susceptible. So, final susceptible population will be equal to solution minus 1 0. In order to calculate the final fraction of population that has been infected, we will use the next line, that is a final infected is equal to 1 minus susceptible. Simple math. Infected is equal to 1 minus susceptible, isn't it? How much is infected is 1 minus how much is final susceptible. Now, we are going to apply vaccination and update the susceptible population. How we are going to do it? By using susceptible after vaccination is equal to finally how much are susceptible, in which we will remove the vaccination percentage from final susceptible population. After this, we are going to return the fraction of population that remains susceptible after vaccination. So, for this we are going to write return susceptible after vaccination and final infected population. After this, we are going to test various vaccination. For example, we are going to write strategies in which we are going to take adjust vaccination percentage inside that particular strategies function, and we will say vaccination percentage is equal to 0.2. For example, 20% vaccination coverage, that is why we are writing 0.2. So, final susceptible and final infected would be equal to simulate disease spread, in which this is a function in which we are giving parameters beta, gamma and vaccination percentage. Now, the moment you do this thing, you will see the results. Now, let us see the impact of our vaccination strategy. How will we see this? How we kind of see things in Python? A simple function, print. What we are going to print? Final susceptible fraction after vaccination, in which we are going to print final susceptible, and we are also going to print final infected fraction, in which the simple output of the variable that we have final infected. So, the moment you print it, you will be able to see things, and in the end it is a triumph of science. And there you have it. By using ODE and Python, you can model the spread of infectious diseases, access vaccination strategies and make informed decisions to protect public health. How big this thing is. But for this you have to keep on exploring. You have to keep on exploring. Never stop exploring our journey through ODE equation. So, our journey through ODE equation will keep continuously, it will keep on iterating. With biotechnology and medicine offering endless opportunity to apply this mathematical tools, whether it is optimizing treatments, understanding immune systems or responding to the global health crisis, ODEs are your companions on the path to discovery. So, dear scientists, friends, students, let us keep pushing the boundaries of what is possible, one equation at a time. Our quest for knowledge is boundless, and with Python as our guide, the future of science is bright and full of promises. Until our next class, keep coding, keep experimenting and keep changing the world. Thank you.